Okay, yeah, I'm talking about the METIS WFSensing strategy for the FDR phase, status and challenges. I'll mention my co-authors in the acknowledgements later. Okay, what we mainly did change from PDR to FDR is that the subaperture size, let's call it, or the number of pixels on the CCD for the pyramid has been adapted in order to fully utilize DM4 correcting capabilities. Long story short, we have now the same specs than the other first light instruments, so METIS finally fits in the picture. Thanks to Carlos for providing this graph showing the frequency range covered by DM4 compared to what a free DM would cover. Why do we compare with the free DM? This is because of the strategy, the reconstruction strategy we do choose, well, we do have right now in METIS, which means, now coming to the wavefront reconstruction algorithm, we have the pyramid operator applied to some residual wavefront equals the measurements. So and now we somehow need to discretize this incoming residual wavefront. Most of you use KL modes or Cernicus or RDM influence functions for this. And we did think of using finite elements to discretize the wavefront. So if I knew nothing about the operator, P, so the pyramid, and assume that the residual wavefront is like really small residuals, not really coupled along the pupil. So we thought finite elements might be good. The community refers to it as zonal. So I really just do to poke the little zones and make it head functions, or bilinear inference functions of a free DM. So this is the reason that we in the slide before compared with this free DM, because the now yellow curve shows what we cover with our ansatz functions for the reconstruction. And this maps the M4 capabilities quite nice. Okay, then we do like what everybody else does, and has been shown before also in the talk of Bernadette. We invert what we call poke matrix, so the system matrix, using MMSA reconstructor, and we have as covariance term for the atmospheric conditions, we have the Laplacian squared, which is easy implementable on that sort of ansatz functions, so the zonal pokes and the free geometry. So you could as well say we did choose this zonal ansatz because we understand how to implement in an efficient manner the reconstruction. Would be true as well. Some remarks on that. We did also play around. No, I'm not supposed to say play around. We did also study the effect of a post-smoothing of the wavefront reconstruction before entering the integrator or some smart-ass control. And somewhat found out that increasing the regularization term in front of the atmospheric covariance has a very similar effect than a temporal control of the reconstructed residual wavefront. They somehow go along. I do more smoothing in the post-processing. Is almost comparable to have a larger alpha parameter than the regularization. Let me mention this alpha in our implementation is not a free parameter. We choose it between 5 to 10% of the maximum entry of P transpose P. So you don't have to worry about how to adapt or adjust this parameter whilst doing observations. So for all atmospheric conditions, no. For all atmospheric conditions, we had a look at, and this is the 5 from very bad to medium, blah, blah, blah. The same alpha parameter was usable. Tuning this parameter gave some minor changes in the quality, but we like to claim choose it large enough so nothing happens and you're safe. And one last point, which is now a pro and a con. It depends on how you see it. The optical gains using those zonal pokes are almost constant, which brings me to the next slide. You're all familiar with the right-hand side plot. So the optical gain or whatever you plot over the mode index or actuator numbering We already know we saw they all did a lot of those presentations. So it's not new from my side, it's already well known. They look like this and they're almost constant, but we have these peaks all over the place, which makes us think it's not really good. Now plotting the same data over the pupil, so on the position where the actuator is, we see that these peaks are, I don't like to call simply, but yeah, simply boundary artifacts. You see them along the spiders, along the central obstruction, so we can handle them quite well. So I don't really see this as a disadvantage. The question, if we with this zonal approach can have the same correction capabilities in terms of optical gain than applying optical gains on modes, somewhat is open, but you know, we are METIS, we're in K-band, so we cool. Okay, the full control scheme for METIS is, we have the wavefront reconstruction, as said, optimal basis, I put it in brackets. If the basis is good enough, it fulfills all the requirements, so we stick with it. In a second step, we hand over the reconstructed residual wavefront to the controller, and the temporal control is done in a suitable control basis. And the final step is projecting the desired DM shape on M4 and on the M4 basis, modes, whatever. So this is the status right now. Let me mention that this is not yet fixed. It's the status right now, and there are considerations to not have different bases for the 3 steps, but have one basis. This is something that Carlos is into it right now, and this is just ongoing, I'm saying. Let me mention that the petal piston, at least in our simulations, and right now, atmospheric conditions, optical gains, all well handled. So we don't seem to have problems right now with this petal piston, segment piston. But honestly, we never had those large inputs that have been presented in the talk before by Christoph. So 10 microns are a game changer, probably. One thing that I'd like to mention especially is use all the pixels you can use on the pyramid CCD. Also the pixels that have very low illumination, so the boundary pixels, and especially use all the subapertures besides and under the spiders. This was for us the key feature to get the piston control stable. Okay, so the ongoing future work. Right now we do somewhat of an inverse crime. We generate our poke matrices with the same forward simulation that we later on use in the simulation. So we have the system is perfectly caught. Our forward simulation just knows what's going on. I did play around a little bit with the discretization of the forward simulation, so really fine sensing. And I mean, it gets extremely slow. The FFTs take not years, but days. And the output of the pyramid really changes with discretization. So we need to have in the back of our heads that once we create artificial interaction and control matrices, we really must simulate our system as close to reality as possible. I mean, it's obvious, but still, let's have this in mind. Yeah, of course, future work is impact of different bases, modes to be used in the reconstruction, as already mentioned. This is ongoing now with Carlos on the team. I think there will be more pushing forward towards that direction. Optical gain studies, of course, and still somewhat not directly on the must-do list, but nonlinear reconstructor. So once I have a nonlinear reconstructor for the pyramid, I don't care about the optical gain at all. The nonlinear reconstructor knows what to do, right? Well, I guess right here. Okay, now thanks. Without special ordering, of course, Julia for giving me all the physics input to the pyramid. Stefan, one of my colleagues, for providing permanent help with Compass and Octopus and well, all the rest. Miska for his especially Octopus help and the fruitful discussions with Christophe Verrenaud. So he puts his fingers on the places where it hurts, and the optical gain discussions with him were really fruitful. Then, of course, the METIS IO team, now especially with Carlos, Ronnie, the boss, and the community. I really like the open way to discuss. I'd like to mention also the guys from the Harmony team, Jean-François and Noah. that they are always open for discussions, and this is something I really like. Of course, it's fighting who's the best, but still it's helpful. That's it from my side.
Okay, thank you, Andreas. Thank you. So I have a quick question for you, maybe a little bit specific, but you mentioned that you want to use all the pixels, even those with very low intensity, right? So you said that's a key point. So my question would be, how do you select the pupil map in your simulation? Do you use a threshold intensity? Do you use nominal values from geometrical abstraction?
It's purely projecting the pupil on the CCD, and each pixel that sees a part of the pupil is taken. So the threshold right now is 1% of illumination, 5% of illumination. So we really do use the pixels.
Okay, and still with 5% of the illumination, you find a stable system.
Yeah. What you should not do is use actuators that have very little signal on your CCD. But using pixel with low signal is just fine.